Hello everyone, and today we are going to talk about the Fermat's little theorem. So this is the statement of the theorem. So let p be a prime number and let n be a natural number not divisible by p. Then n raised to the power of p minus 1 is congruent to 1 modulo p. So we are going to use several technical lemmas that we are going first to give without proofs. So the first lemma is also known as Euclid's lemma. It says that for any natural numbers a and b and the prime number p, if the product ab is divisible by p, then either a is divisible by p or b is divisible by p. Then we have lemma 2, which is basically the same lemma, just in a different form. And it says that if both a and b are not divisible by p, then their product ab is not divisible by p either. So the lemmas 1 and 2 are trivially equivalent to each other, and we give here both of them because sometimes it's more convenient to use the statement in the form of lemma 1 and sometimes in the form of lemma 2. So lemma 1 should be intuitively more or less obvious. It is a straightforward corollary of the fundamental theorem of arithmetic, which states that any natural number can be expressed as a product of prime numbers, and that this expression is unique up to the order of the prime divisors. Although Euclid's lemma sometimes is proved without using the fundamental theorem of arithmetic, because it's a simpler statement than the fundamental theorem of arithmetic. And also, like, if proving lemma 1 as a corollary of the fundamental theorem of arithmetic, then we need to make sure that the fundamental theorem of arithmetic is proved without using lemma 1 to avoid circular reasoning. So now we have lemma 3, which says that if we have the congruency, so AB is congruent to AC modulo P, where P is a prime number and A is not divisible by P, then we can cancel A from both sides and get B is congruent to C modulo P. So this lemma 3 is a straightforward corollary of lemma 1. And so for now we give these lemmas without proofs, but we are going to give the full proofs at the end of the video, but they are technical, and so the viewers are encouraged to skip that part of the video. So now we go back to the main theorem, Fermat's little theorem. And we are going to prove it. So let's consider the numbers n, 2n, 3n, and so on, p minus 1n. So in total we have p minus 1 numbers. So notice that by lemma 2 they are not divisible by p. All of them are not divisible by p. And why is that? So if we pick number I between 1 and p minus 1, then I is not divisible by p because I is strictly less than p. And n is not divisible by p by the condition in the statement of the theorem. Then we if we apply the statement of lemma 2, then we get that I n, so I multiplied by n, is not divisible by p. So now let's prove that these p minus 1 numbers all have different remainders when divided by p. So take two of them, like two arbitrary numbers of this p minus 1 numbers, so in and jn. suppose that they have the same remainder. So like we are proving it by contradiction. So suppose that it's not true that they all have different remainders, and then there are two of them, I, n, and j, n, that have the same remainder. But then, like, if we subtract one of them from the other, so jn minus in, then it's equal to j minus I, all of this multiplied by n. And this is divisible by p. Because if we subtract two numbers with the same remainder, then the result will be divisible by p. So then, but this is a contradiction with the previously proved fact, because we previously just proved that all of these p minus 1 numbers are not divisible by p, and j minus I multiplied by n is also one of these p minus 1 numbers. So this proves that these p minus 1 numbers all have different remainders when divided by p. But also, like, notice that none of them has remainder 0, which we previously proved. Because none of them is divisible by p, which means that none of them has remainder 0. So but there are only p minus 1 such possible remainders, which is 1, 2, 3, and so on, p minus 1. There are no other possible remainders. So it means that these p minus 1 numbers must have exactly these remainders, but possibly in different order. So like, in other words, these numbers, like the remainders of these p minus 1 numbers, is the rearrangement of the numbers 1, 2, 3, and so on, p minus 1. So then what happens if we multiply all these p minus 1 numbers? So the product of these numbers must be congruent to the product of these p minus 1 remainders modulo p. So that's the congruency that we have. And we just rewrite it by regrouping all the n on the left sides. So we get n raised to the power of p minus 1 multiplied by all these numbers. So, and we notice that like, we have on the left and on the right side, we have the same factor. So after n raised to the power of p minus 1, all the rest, the product of the numbers 1, 2, and so on, p minus 1, is the same on the left and on the right sides. So now we notice that none of these numbers 1, 2, 3, and so on, p minus 1 is divisible by p, because they're all strictly smaller than p. And if we apply lemma 2 repeatedly p minus 1 times, we get that their product 1 multiplied by 2 multiplied by so on multiplied by p minus 1 is not divisible by p either. So this means that by lemma 3 we can cancel this second factor from both sides, and what we get is, like, n raised to the power p minus 1 is congruent to 1 modulo p, and this is exactly what we needed to prove. So this concludes the proof of the Fermat's little theorem. So now if you go back to the proofs of the technical lemmas, so lemma 1 is the Euclid's lemma. So by the fundamental theorem of arithmetic, we can express a and b as products of prime numbers. So a, we express a as q1 multiplied by q2 and so on qn, and b as the product of q1 prime, q2 prime, and so on qn prime prime. Like, there is a prime in the index and also prime in the q itself. So where all qi and qi prime are prime numbers, not necessarily distinct. So then, like to calculate the product AB, we get Q1 multiplied by Q2 and so on Qn, and then Q1 prime and so on Qn prime prime. So then, by the fundamental theorem of arithmetic, this expression is unique up to the order of prime divisors. So, like if we find another expression of AB as a product of prime numbers, then this must be just a rearrangement of the same prime number. So now suppose that AB is divisible by P. Now, and let us prove that P must be among either Qi or Qi prime. So if AB is divisible by P, then AB must be a product of P multiplied by some number x, which is a natural number. That's just the definition of divisibility. So then we can use the fundamental theorem of arithmetic to express x as the product of prime numbers R1 and so on Rk, and then we can rewrite AB as P multiplied by the product of these prime numbers R1 and so on Rk. So now we have basically two expressions of AB as the product of prime numbers, and by the fundamental theorem of arithmetic, the expression the expression as the product of prime numbers must be unique. So the two lists of prime numbers, one of them is Q1 and so on Qn, Q1 prime and so on Qn prime prime, and the second one is P R1 and so on Rk. So these two lists are the same up to the order of the elements. So this is just a rearrangement, and in particular it means that the first list must contain P, because P is in the second list, so it must be contained in the first one as well. So, but this just means that P must be either among Qi or among Qi prime. So if P is among Qi, then A is divisible by P, and if P is among Qi prime, then B is divisible by P. So this concludes the proof of Euclid's lemma. So now let's go to lemma 3, which is the cancellation of a factor from both sides of congruency. So by definition, the congruency, like the congruency AB is congruent to AC modulo P, means that the difference between the left and the right side is divisible by P. So the difference AB minus AC is divisible by P. So then we notice that AB minus AC is equal to A multiplied by B minus C, and now we can apply lemma 1 and conclude that either A is divisible by P or B minus C is divisible by P. But A is not divisible by P from the condition in the statement of the lemma, so the only remaining possibility is that B minus C is divisible by P, and this, by definition of the congruency, means that B is congruent to C modulo P. So that concludes the proof of lemma 3, and that's it.